Interfacing digital and analog systems, and we're in section 15.4. Computers are used in nearly every aspect of our daily lives, including business, industrial, recreational, and personal applications. In many industrial applications, the devices being controlled or monitored are analog. It is important to understand the operation of analog to digital and digital to analog conversion processes. And so what we're going to do, we're going to look at digital analog. We're going to also look at analog to digital. And we're going to look at it at a very basic level. The devices that we're typically used in computers are going to be much more complex than these, but the devices we'll look at will give you an idea of how these actually work. One type of digital to analog converter is shown below. And so here we have, this is a digital to analog converter, and notice we have the inputs A, B, C. Now these would be digital. Now we would have, for example, this would be 1, 0, 1, 1, possibly a digital value. And in the final output, we're wanting to have this be represented in an analog type format. Note that the least significant bit has the highest value input resistor. And so if we were to stretch this out, maybe if you had 1, 1, 0, 1, like so, that this first bit would be, this would be the least significant bit, and then D here would be the most significant bit. And we're going to look at this in a schematic on the next screen. But for the moment, here we have our inputs, and we call these weighted inputs because these are going, the resistors here are weighted in proportion to the input value. And what we're doing is we're going to feed these inputs into this op-amp right here, and this is in the inverting amplifier configuration, and the gain of this would be, remember here we have the feedback resistor, we had RF over whatever the value of R1, 2, 3, or 4 are, is going to be sent in, and we will get a voltage proportional to that value. And just as a, let's just take a quick look at these. If we had the R1, the RF value here is 16K. Notice the value of R1 is also 16. So here we'd have a gain of 1. The next one would be 16 over 8. And then our gain would be 2, and then the next one is 16 over 4, our gain would be 4, and then the final one 16 over 2, and the gain would be 8. And so this is our typical binary weighting, and when I say that, we had 1, 2, 4, 8, 1, 2, 4, and 8, and if we had a binary value, say we had, I don't know, a 1, 0, 1, 0, we know that you know the weighting here this would equate to 10. And so what we're going to do here is the voltage of the input will cause a current to flow, and that current will flow. Remember, no current flows into the op-amp. It will flow through this, and this will create a voltage proportional to our digital input. So the first one here is going to create this proportional voltage, and then it's going to be fed into the next op-amp. Now the next op-amp isn't being used to promote gain. The next one is being used more so to so that we can precisely set the value of output. And you'll notice we have a 10K input resistor here, and in the feedback there is 8.2 and 5K. Now remember, if this was 10K over 10K, the gain would be just a gain of 1. But in this case, we have the ability to adjust this, and on the next screen we'll see why that comes in handy. But this second amp is just going to be used for fine-tuning, actually. So this is the actual circuit as it appears in Workbench, and you do have this as one of your schematics. I believe it is circuit 1536. Make that a 15, not a 13. And I encourage you to go there and look at this. And so what we'll see here is here are the input resistors. This is the first amp. This is the second amp. And and here we have our inputs. And as the user, you can go in and you can key in the binary value that you wish, and the A, B, C, and D will be the keys that you'll press to set in a certain value. Now, what I have done is I have turned on all of these. So this is in binary, this is a 1, 1, 1, 1, which would equate to 15. Now, what I've also done is that in the output here, this is the voltage being measured right here at the output, and when I went in and measured that, and then I went in and made an adjustment here, and I adjusted this such that this was very close to 15 volts. So what that equates to is a binary 1 equates to 1 volt, and a binary 2 would be 2 volts, and so on and so forth. And since this is 15 here, that equates to 15 volts. And so this is a very basic digital to analog converter. So we come in with a digital value, and our output is going to be an analog voltage. And notice that this is only 4 bits. So we have this 15 volt possible output, and we have broken that into 15 individual possible outputs. And on the next screen here, this would be the sampled output, and you'll see here we come in, and we have one-step increments, and this would be binary 0, 0, 0, 0, and this would be binary 1, 1, 1, 1. Now, you'll notice that this doesn't look and when we think of analog, usually we think of continuous change, something like this, and when we have a digitized output that comes from an analog value that source is a digital value, it isn't as as sinusoidal as we might think. And in fact, if we converted this to analog, if we were doing a sine wave, the sine wave might kind of appear kind of like this. It isn't a perfect sine wave. And now if you get many bits, it gets better, but it is never, it's never going to be the perfect continuous change that you see in true analog. And this is one of the complaints that that audiophiles will make. They'll say, well, digital music will never be as good as analog, and this is the reason why, is because when you go from digital to analog, as many bits as you add, it is never perfect. Okay, this is a example of a digital to analog converter. There are many different forms of these, and typically, this is only a 4-bit one. In music, usually they're up to at least 24-bit recordings, which actually, for my ear, I can't really tell the difference, but I guess there are those out there that can. But this is digital analog conversion, and there's our simplified circuit. And we've introduced this. Next section we'll go the other way. We'll go analog to digital.